Okay, so some definition stuff about solutions. Going back to the beginning of the year, talking about the two types of mixtures. You see up here, a solution is a homogeneous or homogeneous mixture of two or more substances in a single phase. What was the other type of mixture that we've talked about before? Yes? Heterogeneous. Remember, those are the ones where you can actually see the particles in the mixture. In the homogeneous or homogeneous solutions, you can't ever tell what is what in there because it looks uniform. It looks evenly distributed, okay? In a single phase. So here you see separately they have the water in the beaker, and then they have the salt over here. Remembering that a salt can be any type of ionic compound out there, any type of ionic compound. And when we put the two together, the water now looks blue. The salt was blue, so the salt particles dissolved in the water, but we can't actually see them anymore. They're now evenly distributed between the water molecules. Okay, and you can see them right here too. Up here, the yellows obviously must be the negative one because you see the two hydrogens of the water facing inward. These are two hydrogens right here facing inward. Towards that the yellow must be the anion. And then over here, the white ones in the little circle there, the oxygen side of the waters face inward because that's the negative side. So this must be the positive ion. So this one, the yellow would be the negatives, anions, and the white little dots up here are going to be the cations of the ionic compound here. Okay? Now, two other big words you must know. One of the constituents usually regarded as the solvent. Solvent, and the others are called the solutes. Now, the solvent's usually the one that's in the more massive amount, more abundant amount. The solutes are usually the smaller amounts that dissolve in them. Okay? And we're going to look at a few combinations now from this lovely chart. Solutes, part of the solution being dissolved. Solvent is the one doing the dissolving. And the solute plus the solvent is going to give you your solution. But as you see over here on our chart, there's lots of different ways you can create a homogeneous mixture or solution. Solid, okay, are alloys. Alloys are mixtures of metals. Usually they've been melted down and mixed together. So you get things like brass, which is like copper and zinc together. You get bronze, you get sterling silver. Even like the gold jewelry we wear is not pure gold, it's an alloy. Okay? Stainless steel, other things like that would be under the alloy category. Solid liquid, we're pretty familiar with that one because that gives us our Kool-Aid. Gives us lots of our drinks. Okay? Salt water, of course, don't want to drink that though, that's kind of gross. Gas in the solid is a pretty obscure one, okay? Not very often does that happen. So hydrogen and palladium, and it just stores the hydrogen there. It's very obscure. Not a typical one we see very often. Liquid though, beer, gasoline, isopropyl alcohol, the stuff that you keep under your sink for cleaning out cuts has water and the alcohol in there together. My favorite, of course, you all know this, is the gas-liquid combination, because you know I love my Coca-Cola sodas. And we put the carbonation in there, make it nice and bubbly. Okay. Gas, this is one they like to ask on the SOL, gas. For the air, okay, remember air is mainly 78% nitrogen with about 19% oxygen, and then lots of trace gases like 1% argon. A little bit of carbon dioxide, carbon monoxide, sulfur dioxide, nitrous oxide. There's lots of gases in the air, some helium, you know, there's trace gases out there. But we can't pick out which one's a nitrogen, which one's an oxygen, and so forth. So we can't really tell. That's why it would be under the solution type idea. And then this one I'm not sure you're familiar with because this might be back from my day because they don't use these very often anymore. Amalgams. Dental fillings, you know, the ones that were like silvery, they had mercury liquid in them into the solid. Most people use the resin now, so they're nice and they match the teeth, but that would be an example of that kind as well. So, some more definitions. Saturated and unsaturated. This is on your sheet there as well. Okay? Saturated is when you put the maximum amount that can fit in between the water molecules in the solution. Okay? Unsaturated means there's still more spaces, so you can add more. Now, you know when you were a child, or at least back in my day, it was the Tang. I liked the Tang. Anybody heard of Tang before? It's like the powdery orange stuff. I could eat it like it was a fun dip. But, sort of like Kool-Aid. Thought it would be really great to make some really, really concentrated Tang where, you know, they tell you a certain amount you're supposed to put in the water. Well, I kept dumping it in there, right? Because I thought, oh, it'll taste better if I keep adding more, right? You've never done that with the Kool-Aid where you keep adding the sugar, right? Thought it might taste better. What happens if you keep adding more and more? Yes? Yeah, so what do you see happening?
There's a high concentration ratio of the powder to the water.
Yes, so once again, there will be more concentrated, but what do you actually see with your eyes? Yes. Correct. The rest of the powder just falls to the bottom and it doesn't actually dissolve in there. So you get to a point, the saturation point, where it can't take any more in, so it falls to the bottom, and now you're gone into supersaturated area. Supersaturated solution is where you've added more than it can actually hold. Now, what you can do, though, with most salts actually can dissolve more if you increase the temperature. So if you up the temperature, which you'll see on our solubility curve, changing the temperature can allow you to dissolve more for some things, most salts, but some things actually decrease in solubility as the temperature goes up. So we're going to take a look at that solubility curve, and you can go from there. Supersaturated solutions, like, say for instance, I wanted to add more sugar, and people, they do this with sweet tea too, when they make sweet tea, is they have to heat it up to add in the extra sugars and stuff in there, making lots of like the drinkable solutions. They make them super saturated, so they'll heat them up, get them to dissolve more in there. Okay, then if you cool it down, though, it will stay and it will look completely uniform until you add a seed crystal. A seed crystal then would start a chain reaction where it's the solution, all of the crystals would start to fall out, all the extra stuff. I'm going to try to set up that demo for next week so you can see it actually happen. Okay? So we would create a supersaturated solution by heating it up. And then when you cool it down, the stuff will stay in there until you disturb it. You disturb it, then the extra solute will fall out of solution. Okay? So supersaturated is a possibility. One example here, supersaturated solution, is the sodium acetate heat pack. Okay? Put a bunch of stuff in there, and when you break the heat pack, the chemical reaction occurs and you get some warmth out of it. Now for the solubility curves, which is on your paper, you'll see this curve here. The line represents how much can be dissolved in a saturated solution. So each line is really the saturation point. Okay? Anything added beyond that will dissolve and won't dissolve and will remain a solid. It'll be supersaturated. So here, if I'm looking at this line, this is the sodium nitrate line. Okay? At 40 degrees, I can dissolve about 100 grams in 100 grams of water. So this is out of 100 grams of water. I could actually add 100 grams of this and it would dissolve. But if I try to add more above the line, that would fall to the bottom. If I try to add less than the line, under here it would be in the unsaturated category. So under the line is unsaturated, over the line would be supersaturated, and on the line is the saturation point. Okay? So if you want to, make note of that, under the line it's going to be unsaturated. So you could still add more, obviously. on the line, that's saturated. And then above the line is when you're going to get supersaturated. And if it's not warm enough, it will just fall to the bottom because it won't be adding more in. Now remember, this is out of 100 grams of water, this particular chart, the one on your sheet, okay? These are the temperatures down here. So you want to look here, you know, at 80 degrees, how much can sodium chloride dissolve? About 40 grams. Okay, if I'm at 60 degrees, how much can be dissolved in the potassium nitrate? Well, that's about 90 grams. One interesting curve on here that you should note is this guy, ammonia. Ammonia is a gas. NH3 is a gas. Okay, what's going on with its line? It's decreasing. Good. Ammonia is decreasing as the temperature is increasing, and it's a gas. Okay? So, some things, as the temperature increases, will become less soluble. So, let's think about this and what we know about our daily lives, and especially me and my Coca-Cola example here. Because I love my Coca-Cola. Dr. Pepper's pretty good, too. There's some other good ones out there. But let's think about this. We know this from our own daily lives. I put a can of Coke in the fridge all night. I have some left out in my garage or whatever, just waiting around for space in the fridge, correct? If I took one that was cold and one that was just waiting in my garage or in the house that was at room temperature, and I opened them both at the same time, which one of them is going to go flat first? Yes. The one at room temperature, right? It goes flat quicker. The colder one keeps the gas in there longer. Remember, gas particles move pretty quickly. They're moving around pretty quickly. So who's going to escape faster, the warmer or the colder? Warmer, because they're moving faster, so they'll escape quicker, so you will have less carbonation in there. And this kind of is an analogy for why gases, they end up decreasing solubility as the temperature increases because they can escape faster. They're moving faster. They say bye-bye to the liquid. Okay? So now we're going to work some problems on your solubility curve. So let's take a look at that. All right. So we're going to do some reading on our solubility curve. And as you see on this sheet, it provides you lots of the definitions here. Solvent, solute. Talked about these. Solubility, the amount that dissolves in a given quantity. And here our given quantity is 100 grams of water that we're dissolving in. Solubility can be increased by stirring the temperature surface area. But for the most part, you'll notice that gas solubility decreases as the temperature increases. Saturated solutions, we talked about that. That's the maximum amount you can put in. And unsaturated still means you could add more. Okay? So all of those definitions are there for your study. Now looking at our curve here, basically going to read the graph. I'm going to go over one other example at the bottom there, and then let you spend about 10 minutes finishing them up. So if I'm looking at potassium nitrate at 70 degrees here, so I go over to 70, I go up to the potassium nitrate line, which is right about up here, okay? How much will dissolve in the 100 grams of water? If I go and just go over here, which is probably right around somewhere up there, what's a good estimate for that amount that can actually dissolve in 70 degrees? 128 something. It is definitely above the center there. So we go up like 127, 128. Okay, something like that would be a good estimate. Okay, now the NaCl at 100 degrees. So we would go up here to the NaCl line. That one's pretty easy because it's right on a grid there. So how many grams of NaCl would dissolve? 40. And look at ammonium chloride. Ammonium chloride, we're looking at 90 degrees. So at 90 degrees, where's the ammonium chloride connect? What would that be about? 65. Good. Now, looking at all three of these guys, determine which of the above three substances is most soluble at 15. So we go over here to 15 degrees. Looking at our lines here, here's sodium chloride. Here is the potassium nitrate line. And then looking at the ammonium chloride line is about there. So out of those three, who's the most soluble at 15 degrees? NaCl, very good, that's correct. Okay, so a lot of these questions are pretty easy just reading the graph, but you know the SOLs are famous for having graph and chart questions on it. I do want to look at one down below though, just real quick. So I have to do it like this. Let's look at number 6. Take a look at number 6. It says a saturated solution of potassium chlorate is formed in 100 grams of water. So it's at the saturation point, the line. So let's look at that and see where we're at potassium chlorate. So potassium chlorate is this guy. So we are at 80 degrees. So if the saturated solution is cooled from 80, so which is right here, to 50 degrees, okay? So at 80 degrees, how many grams do we have there that we can dissolve? There's 40, right? At 80 degrees, we have 40 grams. Now we're going to cool it to 50 degrees. So how many grams can it now hold at 50 degrees? About 20. Good. So how much is going to fall to the bottom then? 20 grams will fall to the bottom because it can't hold that anymore. It's now not warm enough to hold that. So 20 grams of the little crystals will fall to the bottom. Okay? So now I'd like you to do 1 through 9, or finish the rest of them there. Give you about 10 minutes, and then we'll come back. Okay, so let's take a look at some of these down here. Go over some. Which salt is the least soluble in water at 20 degrees? Obviously, I have it on freeze still, so hold on a second. Let's unfreeze that. There we go. Okay. So, which salt is least soluble at 20? If we go to 20, what's the first line? KClO3, potassium chlorate. Okay, remember all of these up here that are ionic are considered to be salts. This one here, ammonia, NH3, is a covalent compound. How many grams of potassium chloride, that's this guy over here, potassium chloride can be dissolved in 100 grams of water at 80 degrees, right? 80 degrees. So we go up here at the 80 mark, how much? About 50 grams, good. At 40 degrees, how much potassium nitrate can be dissolved in 200 grams of water? Now we know this is out of 100 grams of water. So let's look it up at what it would be out of 100 grams of water. So 40 degrees going up to potassium nitrate, which is right around here. So what would you estimate that to be? It's a little bit above 40. Like 42. So 42 is out of 100 grams of water. So what would we need to do to that to make it out of 200 grams of water? Multiply it by 2. So that'd be about 84 grams. 84 grams of potassium nitrate could be dissolved in there. All right, which salt shows the least change in solubility from 0 to 100? Yes, ma'am. Sodium chloride is correct. Why do we know it's sodium chloride? The line is the flattest. It doesn't have much of a slope. So the slope not increasing a lot means it's not going to change very much. So that's why we would say sodium chloride, because the slope of this line is very flat. It's a flat line. Doesn't really increase that much as you add temperature to it. Now, how many grams of sodium nitrate can be dissolved in 50 grams of water? That's very similar to number 3 where we did the 200 grams. So first, let's figure out how much it would be for 100 grams of water. So at 50, we go up to the sodium nitrate right here, right? That's at 50, going up there to this point right here, okay? How much is that about? It's a little bit over 110, so somebody give me a nice estimate. 112 sounds good to me. And since that's out of 100 grams, what should we do to our 112? Now divide it by 2, which would give us 56 grams. Good. How many grams of sodium chloride, this is now number 8, come out of solution when it is cooled from 95 to 30? So let's look here from 95 to 30. Here's about 95, which is about how much? 40 grams minus, now we're going to go to 30. The sodium chloride line is about here. So how much is that? Around 38. Good. So that would be about 2 grams of salt that falls out of solution for number 8. And last but not least here, number 9. Why? Why does ammonia decrease in solubility from 0 to 100? Because it's a gas. Okay? It's a gas. I guess I should write, it's a gas. There you go. Gases usually decrease in solubility. Okay, so now let's take a look here, talking about molarity. Flipping over to the back. Molarity. Molarity is a measure of concentration. This is the concentration measure we use in chemistry. And it always, always, always is the moles of the solute divided by the liters of the solution. And then it gives you molarity, which is a symbol, its unit is a big M. Okay? So the amount of solute that can dissolve in the liters of solution is given its concentration value. Okay? We're going to use this equation in order to figure out different concentrations. Now here I have a couple of solutions from the AP lab. I can show it to you real quick. This one that's darker purple, this is called crystal violet solution. If you actually use it to stain cells. This one is 25 micromolar molarity. This one is only 5 micromolar molarity. What can you tell about the two different solutions? What stands out immediately in terms of differences there? The 25 micromolar is a lot darker than the 5 micromolar. Now why is that? Because the one with 25 micromoles has a lot more moles in it per unit volume, per liters. So that's why this one would be a lot darker than this one over here. So we would say, of course, the darker one's more concentrated than the light one over here. The light one is less concentrated. Okay? So keep that in mind. Just like when we're talking about making the Kool-Aid, if you kept adding the sugar beyond the amount it told you in the directions to use, wouldn't it taste a whole lot sweeter? It has a lot more sugar particles dissolved in it. So that one would be more concentrated The one where you put the right amount in would be less concentrated. And of course, if you didn't put enough in, of course, it tastes watery. And then, you know, that would be less concentrated with the Kool-Aid example. Okay, so I'm going to show you an example here, and then we're going to work some problems. Oh, in preparing solutions, too, before we get to the actual problems, basically all you have to do is weigh out and find the grams of how much you need to put in. You would do a grams to mole conversion. And then you would add the water in the amount that you need to make it the concentration. We use these things called volumetric flasks. They have a nice line on there. So this one's a 1,000 milliliter or a 1 liter. And then you can put the other ones in using graduated cylinders to measure in other solutions. Okay? Now, if I had 0.0210 moles of nickel 2 chloride here, dissolved in enough water to make 250 milliliters of solution, how would we calculate the molarity? Well, in the molarity equation, we need moles and we need liters. Do we have moles and liters in that problem up there? We have moles, right here, moles, but do we have liters? No, we have 250 milliliters here. So, since it's not in liters, we have to do a conversion to liters. Does everybody remember how to do that? How many milliliters are there in 1 liter? You remember your King Henry died by drinking chocolate. Oops. Let me write it over here since it's in the way. King Henry died by drinking chocolate milk. This is milli. Base units, liters here. Okay? Who's larger? Liters or milliliters larger? So if it's the one, then we do 1, 2, 3. So that's a 1 with 3 zeros. It's always 1,000 milli in the base unit here. 1,000 milliliters equals 1 liter. Okay? So that's the conversion you're going to use when we are doing these problems. Now, so shown here, convert milliliters to liters. Basically, by dividing by 1,000, you move it 3 decimal places to the left. So 250 becomes 0.25. Now, calculating the molarity. All you have to do is put the moles on top, the liters on the bottom. Plug and chug, we call it. So you do the division. Not forgetting significant digits here. This would be 3 and 3 divided by, when you do the division, you go with the least number, so you would have 3. And don't forget that the big unit or for molarity is going to be a big M. The unit for molarity would be a big M. Okay, so let's do a couple example problems together. So looking here, this is on the back of your paper. And it gives you an example at the top to follow too. Let's look at number 1 here. What is the molarity of sodium chloride if 7.50 grams are dissolved in 500 milliliters of water? So, in our equation, we need moles over liter to give us the molarity. Do we have moles? There's moles up there. I have grams. Do I have moles? No, I do not have moles. So I have to do a quick conversion from grams to moles using my mole map that we've gone over. Then, do we have liters? No, we have milliliters, 500 milliliters. So I'm going to go ahead and divide this by 1,000 real quick, or just move it 1, 2, 3. So that's going to be 0.5000 liters. So we have that value now. For the grams, it's just a straight up mole conversion problem. We're going to do a little T-chart over here. 7.50 grams, diagonal down the grams, going to 1 mole, okay? Let's do the molar mass of sodium chloride. Sodium equals 22.99 off the periodic table. Chlorine is 35.45, its mass off the periodic table. We add those up, and we get 58.44 grams per 1 mole. So the 58.44 goes here. Now we calculate our moles, and what do we get? Get 0.128 moles. Now we can take that value and divide it by our liters over here, 0.5000 liters, and we will get our molarity, which is 0.256, big M for our unit. So a word to the wise as you're doing these. If they give you moles and liters, all you have to do is insert it and divide. If they give you grams, you have to convert it to moles first. And if they give you milliliters, you have to convert it to liters first before you begin. So pay attention to what they give you so you know if you need to do a conversion before you begin the problem. Okay? Okay. Alright, so here for number 2, it's nicely already in liters for us, so we don't have to do anything with that value. We do have to do something with the 25 though, 25.0 grams of the copper 2 sulfate. Somebody like to tell me their molar mass they calculated? Yes? 159.61, is that good? Is that what you got? Okay, so when we calculate that, we get the moles to be 0.157. We divide that by 1.00, so our molarity is 0.157 big M. Number 3, we are given 33 moles, so we don't have to do anything with that number. Isn't that nice? But we do have our milliliters here. We do have to go 1, 2, 3, okay? Since it's 0.33 divided by 0.5. So remember these zeros, because they start from the right, those ones aren't significant. So 0.33 divided by 0.5 gives me 0.66, which eventually will turn into 0.7 M. Okay? And nice and convenient here in number 4, we have moles already of magnesium chloride and liters of water. So all we have to do is a simple division. 0.250 divided by 2.00. And that will give us our molarity, which is 0.125. It even gives it to us in 3 sig figs, which is what we need. So that one worked out nicely. And last but not least here on our number 5, it says 58.44 grams of sodium chloride. So we would need to convert that first. However, we already know this molar mass because we calculated it in number 1. So that's also 58.44 grams equals 1 mole. Okay, so that's going to be 1.000, though. Don't forget that you had 4 sig figs to begin with. That's our moles. Now we can divide it by the liters, which happens to be 1.00 liters. 4 digits divided by 3 digits gives me 3 digits in the end. So don't forget significant digits do play a role here as well. Now let's talk about Dilution. Dilution. All right, dilution of solution. It's a formula. Yes, bless you. M1V1 equals M2V2. So, if I have a stock solution with a certain molarity, I can figure out how much of its volume to add in order to make it weaker. So then you're going to be adding a lot more water in there. So M1V1 equals M2V2 is the equation formula you'll use. Let's do an example to show you what that means. If I have 50 milliliters of a 12 molar solution, so this would be V1 and this would be M1 of hydrochloric acid, and I want to dilute it to 200 milliliters. 200 milliliters, that's going to be V2. What would be the new concentration? That would be M2. So it's basically plug the numbers into the formula, multiply and divide. So if I plug them in, 12 molar times 50, because this is M1V1 equals M2V2. So here's my 200. So you multiply the 12 times the 50, and then you divide by the 200, and you get your new concentration, which is 3. Adding water makes it weaker, right? So we went from 12 molar to 3 molar. Isn't the molarity getting less? Yes, you can mentally check your numbers there. Now let's go ahead and work some problems on your sheet. Once again, you must pay attention to the units to make sure everything matches up. You don't have to keep the volumes in liters for these. You just need to make sure both volumes are the same unit. So if you're using milliliters, the other one also has to be milliliters. Okay? Like for instance in number 6, if you dilute, here's V1 of a 1.00 m, that's M1, solution to 1 liter, this is going to be V2. What is the molarity, M2, of the new solution? Well, we have a volume unit problem here. One of them is in milliliters, the other one's in liters. So we do have to convert one to the other. It doesn't matter which way to go. So would you like milliliters or liters? Change it to liters. Okay, so I'm going to change this one to liters by going 1, 2, 3. So it's 0.5000. Now I can use my formula, M1V1 equals M2V2, and just plug them in. 0.500 liters times my volume, times my molarity, okay, equals, actually I did that backwards, let's rewrite that. The molarity comes first, 1.00 m, times my volume is 0.500 liters, equals M2, which is what I'm looking for, times the second volume, which is 1 liter. So if you multiply the 1 times 0.5, then you divide by 1, your M2 should come out to be 0.500. Big M, 3 digits here, 4 digits here, 3 digits here, so we go with the least number for multiplying and dividing. That's why I keep 2 of the zeros next to the M2 there, 0.500. Let me do one more so you can do some practice. Because number 9 says, to what volume would you dilute? 250, so this is V1, this is M1, the 0.4500 molar solution of NaCl, 2 so that the molarity is now 0.1250. So now I'm missing, this is M2, I'm missing V2. That's the one I need to find. So once again, you just plug them in. M1 V1 equals M2 V2. So M1 is 0.4500 M times my V1, 250, equals M2, 0.1250 big M. And now we're missing V2. So multiply these guys, divide by this guy, and our V2 now is going to be, I believe it's 900.0 milliliters. So that means to make this solution, I'm going to need 250 of my stock solution, the more concentrated one. And I'm going to have to add 650 of water so that it equals a total of 900. Okay, so basically 250 is coming from the stock solution. Then we have 650 being added from the water, so that we have a total of 900 milliliters in the solution. So that's how we figure out how much water to add if we were doing that. Okay? So you have, what, 3 more problems here, and then a few on the back to practice. The first 4 on the back are molarity equations. The last 2 are dilutions. Okay?